So thank you, everyone. Today's topic is 4D technologies for reservoir production management. Today's presenter is Shervin Razulzadeh. He's our principal technical advisor. He has 20 years of experience in the oil and gas industry and has completed a multiple deterministic and geostatistical seismic reservoir projects for the Middle East, Africa, and North Sea. He's also extensively technically knowledge in seismic interpretation and geological modeling, and he provides knowledge transfer, training, and support for clients using several of our software packages: Jason, HampsonRussell, Earth Model, Inside Earth, and VelPro. So with that, I'll hand it over to Shervin.
Thank you, Jasmine. Good day, everybody, and very welcome to our this session of the webinar. So I will start with the brief about the GeoSoftware portfolio, and then a little bit introduction about the 4D and the typical workflows that is used in 4D studies, and then some snapshots which will be shown from the different projects that we have done and have captured into this presentation. So just brief about the GeoSoftware portfolio. Within GeoSoftware, we develop different tools, starting from HampsonRussell. As you may know, it's very famous software, so we use it for seismic reservoir characterizations. Jason Workbench, another one which is for advanced seismic reservoir characterizations. We have PowerLog if you want to do petrophysical analysis, advanced and basic petrophysical analysis in an intuitive environment. PowerLog is for you. Inside Earth for interpreting the faults, fractures, paleostratigraphy, salts in a quick and precise way on the post-stack seismic data and stacked volume or any inversion results, for example. RockSI for building your Rockphysics models, calibrating it, creating a simulation of the Rockphysics data. That is the RockSI. FlowSI, it is for reservoir simulation to seismic. VelPro for velocity modeling, pore pressure predictions using the velocity data. And finally, our Earth Model FT, which is used for reservoir modeling and transferring the properties from seismic reservoir characterization to your reservoir grid and also your reservoir model. But as you know how the 4D seismic works, so we have our base seismic, we have acquired, processed, and interpreted that seismic. We have found the reservoir, and from that reservoir we are producing the reservoir. So there will be some changes in the reservoir. We shoot another seismic, process it, interpret it, and find the differences between the base and monitor surveys, and it will give us the 4D seismic data. Then we need to analyze the changes happen to the seismic data. So could be the movement of the fluid fronts, and we can also map the produced zones and bypass zones using this 4D study. The typical workflows for 4D could be time-lapse modeling, simulation to seismic modeling, 4D calibrations, which is the seismic data calibration, interpretation of the data. So in the time-lapse modeling, we're talking about, for example, estimating the velocity density changes due to the fluid changes or pressure changes in the reservoir, or the thickness changes possibly. And we can create synthetic seismic traces to compare with the existing seismic data and infer what is happening inside the reservoir. For example, predicting the changes that may occur in the seismic data. Simulation to seismic modeling, so we have reservoir models. Reservoir models, they do the production mathematically or based on the computation, and it will give us the final condition of the reservoir. So we can get that final condition or current condition of the reservoir, which is produced, and we can create our synthetic data and match our current seismic data and to see if it is matching our seismic or not. And for the calibrations, comparing the time-lapse seismic surveys at different times, you have different seismic, so you want to calibrate them. They shouldn't be exactly the same because there will be different noise content, different amplitude maybe, and different phase inside the seismic. So we need to calibrate them and compare them to remove those spurious noise, which are not really 4D signals. Once we calibrate the data, then the next step will be time difference analysis of the seismic data, different monitors and the base, or investigate what is the amplitude difference is telling us, and also do 4D inversion for quantitative interpretations. Start from time-lapse modeling. We need Rockphysics model. So for this Rockphysics model, we have this RockSI, which is used for developing your Rockphysics model. Could be a granular models for the clastics mainly, or the cemented clastics, and inclusion models for dense rocks like carbonates. So we can design our rock physics model, calibrate it to the measured data points in the logs, and start investigating what happens. For example, the fluid changes, what we expect to see. For example, the bulk modulus is changing or velocity changing. What could be done in the reservoir? Or, for example, effective pressure changing. What should be the effect of that effective pressure changes on the bulk modulus and the shear modulus from the current situation to the produced situation, which is the pressure is producing. After calibrating our rock physics model, we can generate some synthetic data. For example, which is shown here, the inverting the seismic data and getting the acoustic impedance for monitor and base, and also VPVS for monitor and base, and cross-plotting the ratio of the VPVS between the monitor and base over acoustic impedance monitor and base. And we can put that a rock physics model that we have created, and we can estimate, for example, if there is a, for example, water is replacing oil, the data should be, we should see the data, this fractional data should be around this area, or if increase of the gas saturation is increased, or gas comes out of the solution in the red side, or some other investigation like this, so which will help us to interpret our 4D signals. We can also create synthetic seismic, for example, to investigate pressure, temperature changes. Example shown here, so which is done in the HampsonRussell. This case is creating synthetic seismic data. This is on my reservoir, and the background is the velocity changes. And you see that at different pressures, so each panel has different pressures, starting from 0.5 megapascal to 2.5 megapascal. And I'm creating synthetic seismic at different temperatures. So you see that at the 0.5 megapascal, the temperature changes doesn't change this reservoir velocity. But if I am going to the little bit higher pressure, so I'm able to see that yes, the synthetic is changing, the thickness is changing in time. So this type of synthetic generation will help me to understand what could I expect in the monitor seismic data. Simulation to seismic modeling is another topic which is can be used for 4D studies. So what is the motivation for that? As I mentioned, we are going to validate history-matched reservoir models by recorded seismic data. So we use the current reservoir model. It has produced some oil or carbon, and we have now acquired seismic data. So we want to see if this model is matching the current seismic response. So we can do that using this data. And we can see if it is matching to the recorded seismic or not. This is the workflow. So we have our reservoir model, we calculate synthetic data, and that synthetic, does it match to the current seismic? If yes, that's fine, and our reservoir model is fine, so it's matching our hard data, which is seismic data. If not, or not, so there will be some problem with the reservoir model, or we need to do some maybe processing change as well on the seismic data. We could use this for 4D feasibility studies. So for example, will 4D seismic help production monitoring? Are the production induced 4D effects detectable? So these are the options that we can investigate using this type of simulation to seismic workflow. And sometimes clients want to know, is it a good time for doing a 4D seismic monitor? So using this tool, we are able to identify if we are able to see the 4D signal at a specific time, then yes, we can do the seismic acquisition and processing. The workflow for this is that is another view. So we have our reservoir model with different porosity, and this reservoir model could have a different water saturation and pore pressure at different times, T0 to Tn. We can establish a rock physics model, and using this rock physics models and using this input data, which is pore pressure and water saturation, for example, we can estimate these elastic properties, which we call it, and which is VP, VS, and density at different times. And we add this overburden and also underburden at that, because we want to create long enough to be able to create a synthetic seismic data. And then we convolve it with the wavelets for each theta, and we get that seismic volume for each theta. Then we can compare it with the different, for example, base to different monitors, and we can see that if there is a 4D effect is visible or 4D signal is visible or not. To do that, yes, we have this reservoir model in the reservoir grid. So it is very limited vertically and could be laterally as well, but usually vertically we don't have overburden or underburden as well. So we need to generate that overburden so we can create this overburden layering, and we can fill it with some, for example, the P-wave velocity data coming from the elastic modeling or coming from the seismic velocities. The other thing with this grid is that there are differences laterally. So if you look at the seismic grid, it is denser compared to the reservoir grid, which is sparser. So we need to resample this coarse grid to the this fine grid to be able to create a similar grid to the current seismic grid. The other things to consider is our reservoir models are mainly in depth, so we need to convert them to time. So what we can do vertical 1D stretch and squeeze using, for example, P-wave velocity computed at the elastic modeling steps using the Rockphysics models, or we can input the external velocity field, usually comes from, for example, from the seismic. So we can use that for establishing a time-depth relationships and convert our depth model to a time model using that velocity data. The velocity, for example, is shown here in a reservoir layer. The next step is a synthetic generation. So for synthetic generation, we have options here that uses Zoprits or accurate charts in the 1D convolutional method, because we will have that reflectivity series at each point, and we can also generate angle-dependent signals using the angle-dependent wavelets. So we will have our synthetic, which is pure without any noise. We can add noises to mimic the noise in the earth. So we have two options. Could be static noise. It will be like a breakup in the events. So you see that nice continuous event has been broken up with these static time shifts. Or could be adding a random noise, could be white noise, which is changing the signal to noise ratio or changing the frequency bandwidth, which is shown here. So we have this synthetic data. We are decreasing the signal to noise ratio, and for this case, increasing the seismic bandwidth. So we can manipulate the different situations on the synthetic seismic data. Example shown here, a synthetic generated for angle of the 30 degree. And for the effect, comparing this monitor to the base. So this is our 4D effect, which is shown here, and we are able to see those. But adding signal to noise ratio of 4, so we are still able to see that 4D signal in the right-hand side. But if the signal to noise ratio is reducing to 2, then that 4D effect is missing in this well. So if this is the case for our reservoir and our field, so in that case, for this time of the production, we are not able to see that 4D signal. So it's not a good idea to do the acquisition for that time. Maybe later in more productions, we could also see this signal here, but we need to do that investigation as well. How we can QC the results of this type of simulation to seismic workflow? So we have options to 1D QC at the selected well. For example, we have this reservoir with this amount of the porosity. This is the water saturation variation, and this is the pore pressure variations based on the reservoir conditions. So it will give us this acoustic impedance variation, rock volume variations. And these acoustic impedance variations will give us this synthetic seismic, these red ones, compared to the black seismic. So we are able to QC what will be the effect of that variation in the pressure and water saturation of the reservoir on the seismic data. You can also generate maps, for example, energy, RMS, NRMS, or signal distortion ratio maps. And for example, we can create a histogram of the on the NRMS map from the base minus monitor. So, for example, in this area, we know that there is no reservoir. I mean, the reservoir should not be affected. So we established this histogram, and we know that this histogram is, the average is showing the 3% NRMS, and it is outside the reservoir. If we believe there is no reservoir then, and we see some signal there, so like this, then we need to go back to the reservoir model and check the reservoir model, why it is showing that, for example, reservoir variations there. We are not expecting that there. We can also do depth conversion of output synthetics for direct comparison with the original reservoir grid. And as I mentioned, we can transfer of the synthetic seismic residual into original grid to flag the zones that need to be updated. So we identify some zones that not following this background, so we can flag those zones and go back to the reservoir model and maybe do some enhancement there, check different parameters there. The next item in the workflow, typical workflow, is a 4D survey calibration. This is very important. We have done acquisition at different times, so the 4D signals should be coming out of the comparison between these seismic surveys. So example shown here, so I have base in the left-hand side and the monitor in the right-hand side. The difference between the two is in the right-hand side. After doing a calibration, I am expecting to see nothing changes in the overburden and underburden in the places that there is no reservoir, and should be only in the reservoir and under reservoir. So this will be our outcome after many processes applied. And I don't expect to see much variation in the above or overburden. If there is a variations, could be noise, so could be other things, but we don't expect to see much variations. The typical workflow for conditioning, which we provide as a workflow, suppose we have a base and different monitors. First, we do some cross correlation between the two to find the overall correlation coefficients and shifts. We apply average phase and time shifts to the monitors, and we get monitor phase shifted and the corrected phase shift corrected monitors. Then there should be differences in the bandwidth and the frequency content, and it also could be phase content as well. So we apply shaping filter, and we get the monitor shape filtered. Then the next step could be amplitude normalizations. These monitors are not necessarily have the same amplitude as the base, so we need to normalize them. So we got this amplitude normalized monitors, and we need to remove any static correction which is above the reservoir. So to apply to the monitors to be same as the base. So we will get this X correlation statics and apply it on the monitors. So at this step, our data is calibrated to base. So we will start interpreting the delays, time delays, which is due to the hydrocarbon movement or fluid movement in the reservoir. And we interpret the base of the reservoir and find how much is the time delays at the base of the reservoir between the monitors and the base. So it will help us to interpret the reservoir changes. But other than that, we can also, that was time delay interpretation. We can also interpret the amplitude differences at the reservoir, so on the base of the reservoir. So we need to apply time variant shifts to align the base of the reservoir to the base, from the monitors to the base, and remove the time delays, which is in this step. In that case, we are able to interpret based on the difference of the seismic amplitudes rather than time delays. So we have two options for interpretation: either time delays at the base of the reservoir, or the once we correct for the time delays, we have this option to interpret the differences of the amplitudes. This workflow is provided in HampsonRussell Pro 4D, and it's a workflow base. We have this typical workflow sorted as a workflow. You don't need to follow all of those steps. Could be based on your requirements and decisions, so you can apply any of these or remove and add and other processes. In the property, we have these functionalities grouped under 3 categories. One is QC tools for generating standard 4D metrics. For example, you want to calculate correlation coefficients and shifts between the monitor and base. You can also calculate the NRMS of the differences between monitor and the base, predictability, Taylor expansion shifts, and for example, volume difference itself. And plus other things like cross-class plotting and those seismic data and the slices as well. Those will create some metrics for us, but those metrics might need some corrections. So we apply some corrections or condition those. So that's the next step. Then, for example, we condition the time shifts. Not every time shift is acceptable for us because they have low correlation between the base and monitor. So we need to accept the time shifts which has high correlation. So we can apply those type of, for example, smoothing or removing the non-desired time shifts and interpolate it again. This will be preconditioning. And then we can apply those calibrations, which is the next group under the calibration. So for example, applying shaping filter, RMS factor, time variance shifts, and etc. here in the calibration group. So these are very readily available in the Pro4D, so you can just choose one of them, maybe condition it and apply later on the monitor data. I talked about time variant time shift removal. So I have reservoir, so we are producing it, so there should be some changes in the reservoir due to the flow changes or pressure changes or temperature changes. In depth, the thickness of the reservoir will not change if there is no compaction. And but the time-wise, we will see some changes at the place that we have this reservoir produced area. So this time shift we can interpret, and it will show us that there is something changes in the reservoir. But we need to remove this time shift. So up to here, we have this is the place that we have this data set. So everything is corrected. We have base and monitor calibrated to each other, but we have this time delay in the monitors. We can remove those time delays and monitors using the time variant time shifts applications, which are available here. So for example, you can use conditioned shifts cross correlations, and Taylor series expansion method, which is talking about how the time shifts using the Taylor series in one trace. Dynamic time warping, again, it's applied on the one trace. We have this dynamic vector warping with Gaussian correlation, which is a 3D warping method. Comparing these different methods at, for example, time slice of the base minus monitor, which is time slice from the time shifts. So you see this is for condition correlation, Taylor expansion, dynamic time warping, and 3D vector warping by Gaussian correlation. This specific reservoir is a SAGD or steam-assisted steam-assisted reservoir. They are producing heavy oil from that reservoir, so they know where the steam is injected, where is the production is done. So based on your reservoir, for example, I decide that I see smooth variations in this method compared to the other one, which is very noisy. So maybe it's better to use the last one, which is shown here. We can also compare the NRMS, normalized RMS of the base versus monitor at the reservoir level layer. So again, comparing these 4 options, I can say that maybe this is the best, correction method that I should use for monitoring the 4D signal in my reservoir. Going toward interpretation, so we calibrated our seismic data, so we need to interpret those signal comparing the monitor to the base surveys. Could be time difference, amplitude difference, and 4D inversion. So we can interpret time delays, we can interpret seismic amplitude difference themselves, and we can go for quantitative methods for deterministic inversion and geostatistical inversion. simple, this one. So after calibration, we can calculate, for example, the difference of the time of the base of the reservoir, for example, base minus monitor 1, base minus monitor 2, base minus monitor 3. So you see that how the produced area is getting bigger and bigger with different times of the monitors. That's one way, so it's a simple one. We can also do for the inversion. So this for the inversion will provide this quantitative information. And we can also calculate those time delays, and which is caused by the velocity changes in the reservoir. We need to remove those. We can use those time delays, which is shown here as well, that we have this time delays in time. After applying time variant time shifts, we are just making it flat, and base and monitor will have the same time at the base of the reservoir. We can convert this time delay information into a velocity and add it to the low frequency model to be used in the seismic inversion. Talking about for the deterministic inversion, we can do a simultaneous AVO inversion of the base and monitor surveys separately and compare the results of the AVO inversion. One example is shown here. So first we need to find, for example, my variation in the P impedance is a fluid index. And I need to also know the reservoir index, which usually is a shear impedance, is not affected that much with the fluid. So shear impedance is showing with the sand and shale part. This is a real study from the Southeast Asia. So this will be cut off for reservoir, non-reservoir on the shear impedance. And these cutoffs, these polygons will be showing me different fluid fields. So compare it with the delta acoustic impedance map on in the reservoir layer. So we have this is negative, so between the monitor and the base. So negative, which means that the P impedance has decreased in the monitors, and this blue means that P impedance has increased in the monitors. Comparing with the extractions of these polygons in the 3D, so we have these bodies has been captured, and these bodies are confirmed with the wells, which means these area gas comes out of the solution because the pressure is depleting, and those also confirmed by these purple wells in the map as well. The right-hand side, the polygon is showing the water is coming into the reservoir, which is confirmed also by these wells in the blue one, which is shown on the map as well. So this is one way. So we do inversion for base and monitor separately and find some criteria to separate the fluid, different fluid area in the reservoir. We can do a simultaneous inversion of the different seismics this time. So rather than just separately inverting each of them one by one. So one example is here again, and this heavy oil steam injection is done. So to produce that heavy oil from this reservoir. So we have this. This is showing the reservoir time shifts at the base of the reservoir, and this area is are the horizontal wells has been drilled to inject above and produce in the bottom of that layer. One of the previous inversion done on the reservoir, so you have the top of the reservoir and base of the reservoir. So we have got these blobs. So these are not very interpreters could not relate it to the unconnected blobs. So what are these? So is it a produced reservoir? What is that? So they couldn't do any good interpretation on that data set. So the next step was to use this base and monitor, calibrate and subtract them. So all the calibration process was done, and we got this different seismic amplitude. So we can do inversion on the different seismic. We can get this band limited acoustic impedance and VPVS, for example. And you see that the top and base of the reservoir is illuminated using this band limited time impedance and band limited time VPVS ratios. So what we can do, we can interpret this time and top and base of the reservoir, and there is a contrast between these blue to red, red to blue. We can find this contrast and populate this area with this contrast and add it to the low frequency model, and then add it to the that band limited data, and we get this full bandwidth time-lapse impedance. So it shows that this reservoir, how the reservoirs change in that area. Then we need to interpret the results, and we can compare with, for example, delta T at the base of the reservoir and acoustic impedance variation in the reservoir, which have different measure, independent measure from the current inversion. There was one well here, for example, shown. There is a this green zone here within this this yellow zone. So looking at the well, so it's, for example, this is showing the gamma ray for this gamma ray log, which is showing that this is a reservoir, and this top part is the temperature showing. This is the temperature curve. It shows that temperature is increasing in that place. So that temperature increases causes the bitumen to mobilize, or it's changing the acoustic impedance in that specific part. So it's also observed in that observation well, which was not used for the inversion. So it is confirming the inversion results as well. And the client was happy. They said that for the first time, we see meaningful information coming from for the seismic data. Another way could be for the geostatistical inversion, going further, going for the highly detailed reservoir models. And for this geostatistical inversion, we use the JSON module, which is called RockMod. And we use geostatistical inversion, Bayesian inference method, and Monte Carlo, Markov chain Monte Carlo to create multiple realizations. For this geostatistical inversion, we want to integrate whatever information we have about geology, rock physics, geostatistics, stratigraphy, any trends in the proportions, any trends in the fluid contact, and also how much we believe on the seismic noise. And also we have data. Again, we need to integrate this data with the prior information, so we can combine them in terms of the probabilities using Bayesian inference method, and we find the possible location or probable location for our reservoir model. So we resample that reservoir model using these probabilistic sampling methods. One of them is Markov chain Monte Carlo, and we can get multiple realizations of the elastic properties, which is like P impedance, shear impedance, and S impedance. Reservoir properties like water saturation, or you can name many things: water saturation, weak clay, porosity, and also phases. All of them simultaneously will be calculated for you. Then we can, yes, upscale this to the same grid that we have in the reservoir model. Some attributes of this RockMod or features of this RockMod is very versatile tool, so you can use it for modeling at any scale comparing, for example, to log scale rather than the seismic scale. You can get models in that log scale. Models match well controls your information, your seismic, your whatever information you want to integrate, so it's matching all of those. It can invert to models in depth, and seismic could be in time, so it could be in depth as well. You can invert directly to the engineering properties using the RockPhysics model. You link RockPhysics, the engineering properties to the elastic properties using the RockPhysics models. It can handle multiple vintages or seismic beliefs or seismic data that you input. Could be different monitors, could be different angles, different azimuths, so it can handle any of those. You can build complex multi-level lithophase models. For example, you have sand. Sand is divided to the good sand, bad sand. In the good sand, you have light oil, heavy oil. You can create this type of lithophases. And you can invert directly for lithophases and also the engineering properties. And more importantly, you can also quantify the uncertainty by running the multiple realizations. And also with different scenarios, you can quantify the bias plus the variance of the uncertainty. So these are features. We have other webinars for this and also examples for this. If you want more information, you can contact us too about this. But this is the tools we will use for 4D as well. Example workflow could be route 1, which is invert base and monitor geostatistically, separately to elastic models, and calculate the difference of the elastic models. That's one route, simple. Another route is same as deterministic, use the different seismic data, and which is monitor minus base, and invert using that different seismic. We suggest this a third approach, which is using base and monitor seismic data simultaneously without diffracting them. And we created these models, which is, suppose we have base, and we find the delta properties of the base, added to the base, and we calculate the monitor models. That is how a geostatistical approach will work. For example, we want to find the water saturation and pressure changes, how much the water saturation pressure will be changing in the monitors. So this depends on usually on the porosity and VKLA, which in turn related to elastic properties using the Rockphysics model. So we can link these water saturation, pressure, porosity, VKLA, and elastic properties like VP, VS, and density using the Rockphysics models. We can also define the lithofacies, and we assume that it does not change between the base and monitor, which is the case usually. And we should define our facies that it's not based on the based on the fluid. And as it say, oil and brine sands are modeled by changes in saturation. The lithofacies can be complex and in multi-level with probability trends. So we believe, for example, some facies is, for example, towards north, I have more sandy, towards south, I have more shaly, or vertically as well, and laterally vertically. So example is here. So we have rock reservoir properties, and we create some Rockphysics models. We link those reservoir properties to density, VP, and VS base and monitor. And we have this seismic data. So we are going to invert for elastic properties and reservoir properties using these evidences, which is our seismic data. And also inverting for SWMP. So this will be a little bit complex, but in a nutshell, that we parameterize our inversion based on the base data, for example, water saturation of the base, pore pressure of the base, and we link those to the VPVS and the density of the base on the monitor using this Rockphysics model. Could be Hertz-Mindlin, or depending on the Rockphysics model or the field that we are dealing with. Then the engine will solve for changes of the water saturation and pore pressure in the geostatistical inversion method, and it will give us final results of the reservoir model. So as a conclusion, in a GeoSoftware, we have 4D solutions which are used for calibration of the time-lapse seismic surveys, Rockphysics modeling, and 4D feasibility studies, simulation to seismic modeling, 4D deterministic inversion, and 4D geostatistical inversion. That's almost all. So if there is any question and answer, please type in that box that you have. So if I am able to answer, I can answer, but otherwise I will come back to you later as well. Thank you very much.
Thank you, Shervin. And I think for the sake of time, maybe I'll just go through one question. So let's see, one is, will we be sharing the presentation? Yes, certainly after the webinar is finished, we will share the presentation. One question, Shervin, for you. What criteria do you use to determine if a 4D effect is detectable at the feasibility stage?
Yeah, that's broad actually. So you need to, for example, do the feasibility study. One of the example I showed that with signal to noise ratio, I am not able to see the signal in the monitor or only difference. So could be signal to noise ratio, and you know how it is detectable based on how you can interpret that. Is it interpretable are you able to differentiate between the 4D signal and the background noise? So these are the questions that you need to ask yourself. But usually, yeah, so that signal should be detectable in the different seismic.
Okay, thank you. We actually do have another plethora of questions, but for the sake of time, we can give you a detailed answer after the webinar. And if anybody is interested, we also have more information on where you can find links on our website. So our website, you have a plethora of online resources available to you. Again, I will share these with you guys after the webinar, but if you go to cgg.com/geosoftware, you will find all of these resources there. And also, if you have any additional questions, either directly to the presenter or general inquiries, or even your local software support team, there are some emails listed right here. Again, I will share this with you. But we thank you for your time today. And for the people who ask questions, we will certainly address your questions as soon as the webinar is over. Thank you.
Yes. Thank you, everybody. Bye for now.